So Victor is a graduate student at UNAM's graduate program in philosophy of science, and it is a pleasure to have you here as the first contributor speaker. He will be talking about an intersection between quantum mechanics and cosmology, more in particular, Bohmian mechanics and cosmological problems. Victor, the floor is yours. You have half an hour for speaking, and then we move to the Q&A.
Yeah.
Thank you very much.
Thank you, Maria, Tocha, Andres. And I will talk about Bohmian mechanics and cosmological problems. If you take some class in a faculty of science, maybe you never heard about Bohmian mechanics. Some physicists take it as a curiosity, but I will talk in that it's not the case. So there is a big problem in quantum mechanics, and this related with cosmological problems, but let's go slow. Let's start with the basics of standard quantum mechanics. Usually, we divide the world into two parts, but this depends of a set of rules or postulates. One is we associate a Hilbert space to physical system like atom, electron, superconductor, and we have something that it's called wave function that give us all the information of the state of the system. The observables, the physical properties that we measurement, like position, energy, momentum, it's related with this mathematical object that it's called Hermitian operator. Doesn't matter what it does it mean. And physical states evolve according to Schrödinger equation. We can compute probabilities by Bohr's rule. And finally, if we want to get some particular result, something like position of a particle here or here, we have to measurement. Well, this idea is what divides the world in two parts. In one side, we have the system, the quantum system, that is described by a wave function and then evolves smoothly using Schrödinger equation. And on the other side, we have an observer or a measurement device. So crucially, in this standard view, we get a definite outcome only when an external measurement happens. So this means that the theory depends on a distinction between system and something outside of it. Well, but what changes in cosmology? Well, here's the main problem. In cosmology, our system is the universe itself. And by definition, the universe is a closed system. It contains everything, including the observers and their devices. So we face to a big contradiction. If the system is everything, there is no outside. There is no external devices to make a measurement. So this forces us to ask, if there is no measurement, how does the universe choose a specific reality? How do we go from probabilities to actual facts? Well, let's imagine that quantum mechanics, it's a good description of the world. Let's try to apply the standard formalism to the whole universe. And we can use the math exactly as it is. But without the external observer, the theory breaks down. We find that the usual rules for probabilities don't work anymore. But they are deep inconsistencies that come from the structure of the theory or formalism itself. Well, and how this conceptual tension appear? Well, in cosmology, we cannot explain how the structures we see today, stars, galaxies, planets, came from a smooth initial quantum state. Without a measurement to collapse the wave function, why isn't the universe just a featureless quantum soup? And second, in quantum gravity, well, when we apply the quantum rules to the canonical formulation of GR, general relativity, well, the math implies that the universe is static. It says that the quantum state doesn't change. And we end up with a frozen story, which clearly contradicts our experience of time. So, what do we need? Well, therefore, to do cosmology properly, we need a better approach. We need a theory that doesn't rely on the idea of external observer. We need a framework that gives us an objective description of the universe story, where someone is looking at it or not. Well, as John Bell, a physicist and philosopher of physics, famously said, we are looking for a quantum theory without observers. So, and this brings us to the goal of this presentation. I will argue that Bohmian mechanics is one of the best tools, because there are another, to do this. Unlike the standard view, Bohmian mechanics gives us a clear physical picture. It describes actual configurations, not just probabilities. It works perfectly well without observers. And this allows us to explain how cosmic structure forms and how recover time in quantum gravity. And this solves the problem left by the standard approach. And this will be the whole structure. We will talk about the seeds of cosmic structure, the problem time, the framework or Bohmian mechanics, and how resolve these problems. Well, the idea is the origin of cosmic structure. How do we go from a perfectly smooth quantum state to the complex universe of galaxies we see today? Well, we have a standard picture or story. We usually answer this with inflation. Inflation is incredibly successful. It predicts statistical properties of the universe with great precision. But there is a conceptual gap. Inflation assumes that the universe starts in a symmetric quantum state. The question is, how does a symmetric state turn into specific non-symmetric reality? How does the quantum possibility become an actual galaxy? Well, to understand this, let's look at the math. Well, we start with a scalar field. We start with a scalar field coupled to gravity. Yeah, what is here? And the standard trick is to split the system into two parts. One is a background, which assumes that it's homogeneous and isotropic, perfectly smooth. And the other part is small perturbations on the top of the background. Later, because the background is symmetric, we can break perturbations into independent Fourier modes. Think of each mode as a simple harmonic oscillator. And we have two regimes here. And when the wavelength is small, the subhorizon, the mode oscillates. And when the wavelength gets stretches by inflation, the superhorizon, the mode freezes and becomes constant. So now we can turn these perturbations into quantum operators. We need to pick as an initial state. Since we want to explain the structure, we shouldn't put it by hand. We choose a state that respects the symmetry of the background. And this is usually a Bunch-Davies vacuum. And mathematically, it's a Gaussian wave function centered at 0. And crucially, it looks the same in every direction. Here's the key point. The dynamics of the theory is unitary. This means that preserve symmetry. If you start with a symmetric state and you involve it with symmetric equations, it stays symmetric. Well, so if we calculate the expectation values, the averages, they remain 0. And according to the standard map, the universe should still perfectly homogeneous today. Now you may say, but the state has a width. The variance is not zero. Well, we see here. That's true. The wave function spreads out. But physically, a variance is just a property of statistical distribution. A wave distribution is not the same thing as a rock, a planet, a star, or a galaxy. It's just a wide probability cloud. It doesn't specify where the galaxy is. And this led us to the interpretative leap in the standard cosmology. On the on the left, we have the quantum description, a symmetric state with zero mean. On the right hand, we have cosmological practice, specific universe with lumps and bumps. Well, standard textbooks often identifies quantum variance with classical inhomogeneities. But this is a huge conceptual jump. It breaks the symmetry without providing any physical mechanism to select which outcome happens. And essentially, this is the measurement problem in the foundations of quantum mechanics, but on a cosmic scale. In the lab, we say the collapse, when a collapse happens, is because we make a measurement. But here, the universe is a closed system. So what plays the role of measurement? What selects a specific shape of the universe if there is no observers? Without an answer, the transition from quantum to classical regime is unexplained. Now, let's look at the second problem, the problem of time in quantum gravity. Well, in classical GR, general relativity, time is flexible. Because of diffeomorphism, invariance, physics doesn't depend. Physics doesn't depend of the coordinates. And when you move to the Hamiltonian formulation of GR, this symmetric implies that Hamiltonian is a constraint. It's weakly zero. And classically, this means that time is relational, and the idea that it's not an absolute clock. Well, now we can quantize this. We follow the Dirac's procedure, and the classical constraint becomes a quantum operator, and we get this equation, what is called the Wheeler-DeWitt equation. Here, the Hamiltonian annihilates the state, and this implies that the quantum state of the universe doesn't change. We get a frozen universe, but what does frozen really mean? It means that the wave function is valid all at once. There is no time parameter, there is no before and after. We are left with a block of universe, a static description of all possibilities, but not an actual story. And this creates a gap between classical and quantum views. In classical GR, we have a clear story. In Hamiltonian formulation of GR, we foliate the space-time. So the dynamics is what changed or how information changed between a hypersurface to another. And we have a movie of geometries involving of time. In quantum gravity, we have a single picture. We don't know how to reconstruct the movie from that static picture. So if we want to summarize the problem of time in quantum gravity, the question is simple. If the fundamental theory is timeless, where does our experience of time comes from? How does changing, evolving world emerge from a frozen equation? Well, now what do we need to resolve this? What is missing? Well, in cosmology, we often hear about decoherence as a solution. But as Sudarsky and other philosophers and scientists have pointed out, decoherence only suppresses interference. It explains why don't we see quantum effects or superpositions, but it doesn't explain how a single outcome is selected. It doesn't turn a probability cloud into specific reality. Now, if we want a fully specified account of the emergency of cosmic structure and recover this temporal structure in quantum gravity, then the standard formulation of quantum mechanics cannot be maintained. So this is basically the idea in the foundations of quantum mechanics, that we have the measurement problem. And what you see, what you can see here is a form to systematize the measurement problem in what is called in literature Modelin's trilemma. We have three assumptions that cannot all be true at once. We have completeness, unitary dynamics, and single outcome definiteness. Completeness is a property of the standard formalism. The wave function provides a complete description of the physical reality. Unitary dynamics, it's not a statement of the standard formalism, because we have this postulate, this collapse postulate. So the quantum states not always involve via Schrödinger equation. And we have single outcome definites. That's the idea that we have not macroscopic superpositions. So we have, we have to give up one of them. And if we want to keep a realistic view, meaning the idea that the universe exists objectively, we have two main paths. One is objective collapse theories. We change the Schrödinger equation to force a collapse, and we have models like GRW, CCL, well, and the other is Bohmian mechanics. We keep the equation, we have more variables, particle fields, and we see that in quantum gravity, it's three geometry, and to describe the reality. So the idea for this work is choose Bohmian mechanics. My goal isn't to prove that Bohmian mechanics is only truth. I want to use it as a concrete tool. I want to see if adding a clear physical configuration allows us to solve the structure formation problem and the problem on time. That's the idea. Now, let's move to the solution. What exactly Bohmian mechanics add to the picture? And the core idea is simple. This is the structure in non-relativistic Bohmian mechanics. In a standard quantum mechanics, the standard quantum mechanics only give us the wave function, what is called psi. In Bohmian mechanics, we add some crucial thing, an actual configuration. We postulate that particles have definite positions, something that doesn't happen in standard quantum mechanics, and particles have positions, definite positions at all times. These particles move according guidance law, guidance equation, and we don't need a collapse postulate. The particles just moves. This is a technical concept, the local variables, the idea that that theory needs something like entities that live in some region of space-time independent of our measurements or observations. Oh. But you may ask, does this change predictions? No. If we assume the initial configuration is distributed according to the standard Born's rule, what is psi squared, the dynamics will preserve this distribution forever. So we get the exactly same empirical results as standard quantum mechanics. And here probabilities represent our ignorance of initial positions, not a fundamental lack of reality. Okay. And a common misconception is that Bohmian mechanics is only good for non-relativistic particles. This is incorrect. The framework is flexible. We can extend it to relativistic fields even to canonical quantum gravity. So if in quantum gravity, the configuration is not particle position, but the tree geometry of space itself. So guiding principle remains the same. A wave function plus an actual configuration governed by a deterministic law. And now we can solve the problem. Remember the paradox. The wave function is symmetric, homogeneous. In the standard view, this is a dead end. But in the Bohmian view, we distinguish between the wave function and the actual field. Even if the wave function is perfectly smooth, the actual field configuration, what you see here, is not. It is a specific realization, and the symmetry is broken simply because the configuration exists. And there are models. They are a physical mechanism and math models. And we use the modes of the field, and they follow a deterministic trajectory driven by the wave function. We don't need an observer to measure the universe, and the dynamics naturally drive the field from a homogeneous configuration. The seeds of cosmic structure are in the fields that are non-symmetric. They are there objectively waiting for gravity to amplify them. And let's look at the problem of time. In canonical quantum gravity, we saw that the Wheeler-DeWitt equation gives us a frozen universe. The wave function is static. In Bohmian mechanics, we can solve this problem. We distinguish the generator of motion, the wave function, from the object that moves, the geometry. The wave function is static, but the geometry involves. The equation you can see here describes how trimetric changes. Well, but why accept a static wave function in a dynamic universe? Well, you can think it in this way. In classical mechanics, the Hamiltonian doesn't change, it generates motion. In this framework, the universal wave function acts like a law of nature. It's not the state of the universe, it's the equation that guides the universe. The problem of time arises only if you mistake the law for the state. And we can recover Schrodinger's time. The universal wave function is static, but the geometry of the space is evolving. So we can use this evolving geometry as a physical clock. And if we condition what you see here, the wave function on this trajectory, we can recover an effective Schrödinger equation for the matter inside the universe. So time emerges from the dynamics of gravity. This brings us to my conclusions. So I argue that applying standard quantum mechanics to the universe leads to deep conceptual tensions. But by using quantum Bohmian mechanics, we show two things. We can explain cosmic structure without observers, and we can recover time evolution even if the fundamental equation is static. The gain here is explanatory coherence. We make the theory make sense. And take-home message in this. In quantum cosmology or the use of or foundations of quantum mechanics in cosmology, foundational assumptions are not just optional philosophy. Your choice or ontology, what you think exists, directly determines whether you can explain the origin of galaxies or nature of time. Bohmian mechanics is a proof of the concept that these problems can be solved if we have a clear picture of reality. And finally, this is not a finished theory, it's a research program. Future works includes applying this to more realistic models, understanding singularities and black holes, and seeing if deviations from equilibrium could lead us to new cosmological signatures. And these questions sit right at the exciting intersection of foundations, cosmology, and gravity. So, thank you very much.
Thank you, Victor. Now let's move to the Q&A. Yeah, let's clap for the speaker reactions and clapping. And now let's move to the Q&A. If you have questions and you are in the Zoom meeting, go to the reactions button, raise your hand, and we are going to list you at this point. I think it's Andres and Esteban second. And if you are watching on YouTube and you want to ask a question, just type it in the chat box. Now, Andres, please.
Hi, Victor. Congratulations for your talk. I want to ask, I got a little bit lost in the maths and I kind of lost the main message. Are you arguing that Bohmian mechanics is the adequate algorithm to solve, the adequate theory to solve the problems, or that we need to posit novel particles, that we need to get rid of inflation? What would be your take on this?
Okay. The idea is that in foundations, the idea is that we cannot work with ambiguous formalism like quantum field theory, standard quantum mechanics, because they are a formalism to predict things, but doesn't tell us nothing about what exists. So if we talk about, there is a scalar fields, there is something else without a clear ontology, we really say something about the world, or are just in these theoretical terms? And the idea is that start with a theory with clarity, with a clear ontology, like collapse theories, Bohmian mechanics, and if we need some new scalar field or auxiliary field, we can use it. Collapse models use novel fields to regularize energy or something else. So if we want more fields or something new, we can do it and use it. But the idea is let's start with a theory with clarity, with ontological clarity, and let's see what happens. It can explain, it can do novel predictions. It seems that in collapse theory there are novel predictions, but also in Bohmian mechanics. And that's a little idea.
So sorry, pinky question.
Yes.
Bohmian, your claim is that Bohmian mechanics is the appropriate framework. It doesn't matter what physicists posit. You keep the particles posited. You just give a new framework. That's right.
Yeah, that's the idea.
Excellent. Thank you.
Now, Esteban, please.
Hi, Victor. Thank you for your talk. I have a question about the assumption on the universe as a closed system. So if you could say something more to motivate that, and if not maintaining that assumption would affect your argument in a sense. Thank you.
Yeah, of course. The idea is that if we take seriously standard quantum mechanics, the quantum mechanics that we learn in a science faculty, the idea is that we have something like a quantum state and a classical environment. We have a system like electron, an atom, that could be described by a wave function. And it has something like these distinctions like quantum, classical, quantum system outside. And that's a problem. That's a problem when we try to apply this to cosmology. There is the idea that we have a closed system. It's not the only one we can use. John Bell say something like an observer is something with a PhD, or the first is the first living entity, and that's the idea. It's an ambiguous concept. So if we want to explain and apply quantum mechanics to something like the beginning of the universe, who makes a measurement? There are no observers in the beginning of the universe, and that's the idea. Not just the idea that we have a closed system. Also, the idea that what is an observer in an early universe, or in a later universe? It's an ambiguous concept. That's the idea.
So, may I follow up? Just
Yes, please.
Yeah, but my question was more focused on the notion of a closed system. But as I understand, you start with the traditional idea that we have an observer and a system, and then if you want to apply that to cosmology, since we don't have a plausible observer to assume, then we start with the assumption that we only have the system, right? But why? I mean, it couldn't it still be a physical, an open physical system, just with more? I don't know. Maybe it's part of perhaps yeah, it's part of a problem of defining a universe in a conceptual sense. But
yeah. I think I'm talking in idealized way, because if we associate if we associate a wave function to the whole universe, and that's not a clear idea. And you're right, but the idea is simple. If we have all things here, including measurement devices, observers, humans, that collapses the wave function. If we have something like a superposition, what breaks its superposition? Well, in a physics lab, the idea that we have an external, and that's the idea of the ambiguous and the ambiguous language of quantum mechanics, of standard quantum mechanics. We need an outside to break the symmetry, and we have now this or this, just when we make a measurement. But in cosmology, this makes no sense. That's a little idea, more than try to define what is a closed system or something like this. The idea is we can apply this kind of statements of quantum mechanics to the cosmology. The idea is no.
yeah, thanks.
Yeah, thank you.
Thank you very much, Victor and Esteban. Sergio, please.
Yes, thank you, and thank you, Victor, for the presentation. I have one question that stood with me along the keynote, and is this one. You said that in quantum mechanics, in standard quantum mechanics, there's this problem about time, right? So it is the conceptual problem. So my question is, if this no time assumption is stated by the theories in quantum mechanics, and if it is so, why because as I understand, particles are always moving, right? So like I am not understanding very well where the problem of time arises.
Yeah. Well, we have these regimes: gravity, well, GR, big systems, and quantum mechanics. We have standard quantum mechanics, non-relativistic quantum mechanics, and relativistic quantum mechanics. And our theory or actual theory is quantum field theory or the standard model of particles. We have these two regimes, quantum mechanics and GR. The idea is that this standard, let me, can you see the screen, ¿verdad?
Yeah.
Are you?
Yes.
Standard approach of quantum gravity. We have this standard approach of quantum gravity. The idea of how we can relate it, GR, with quantum mechanics. So we have this GR and quantum mechanics. How to relate it? Well, we have a standard approach. This standard approach takes these standard techniques that works very well in quantum field theory. So we have Maxwell's theory that are fields. If we quantize, we get in this idea quantum electrodynamics. We get to a quantum field theory. And the physicists in this standard approach of quantum gravity says, if we quantize GR, because gravity and space-time is a field, why we can quantize the idea that we associate something like operators, like in quantum mechanics. But when we do this, we get a fundamental theory of reality with no time parameter. If I haven't the Schrodinger equation here, well, in standard quantum mechanics, the idea is that the systems and the state of systems evolves in time. In GR, we have the same idea when we use this canonical formulation. We foliate the space-time in hypersurfaces, and the idea is that the information changes in time. This is the idea of this is the idea of 3+1 formulation of GR. When we do that, when we try to relate it, GR, with quantum mechanics in this standard view, with a theory that doesn't resolve the measurement problem, that is an ambiguous formalism, we get this fundamental equation with no time, with no time parameter. So that's the idea. In a fundamental level, if we accept that quantum mechanics is the good theory, well, we get a universe, a frozen system, a frozen universe. And the problem of time is the idea, if this theory, that I think is wrong, says us that in a fundamental level, there is no time, how do we recover our own experience of evolution of particles, of evolution of objects? And that's a little idea. Can I resolve your question?
Yeah, thank you very much.
Sure.
Thank you, Victor. There is a question from Facebook that says, one could take the instrumentalist attitude and argue that a simple organization of the data is enough. What kind of argument could one give to counter this one?
Can you repeat it?
Yeah, but you can also read it in the chat. So one could take the instrumentalist attitude and argue that a simple organization of the data would be enough. What kind of argument could one give to counter this one, or to respond to this one?
Okay. Well, the idea is something like we have two commitments, a realistic commitment and an instrumental commitment. The idea is that you can be an instrumentalist about about scientific theories or something like that. But if you take this attitude, if you say, oh, quantum mechanics works well, quantum field theory works well, you get these problems. You get a lot of problems. Well, I don't talk about it, but if we apply quantum mechanics to later times, we get the Boltzmann brains, and we have the problem of time in quantum gravity, the paradox of lost information, and that's the idea. That's the idea why I choose some realistic commitment. We need a theory that explains or try to explain the world as it is itself, and not just the idea that something works. It's something like a physical intuition. Newton talks about what exists in the world. Maxwell tell us about what exists in the world. There are fields, there are particles in Newton's world, and it's something like a physical instinct that we need a theory that tells us something about the world, independently if we make a measurement, we observe, and that's the idea. Not just only try to recover some data and it works. It's something like that. It's a big philosophical discussion in between scientific realism and instrumentalism.
Thank you, Victor. Then I have a question, and I think there is no more questions. We'll see. But so I was wondering, it's related to this, whether the cost of this trade is not too expensive. Because on the one hand, you are motivating the shift to Bohmian mechanics, even if just methodologically to try out an alternative. You are motivating this, but the fact that cosmology doesn't seem to have measurements or actual observers. Yet, what happens when you do this shift to Bohmian mechanics is that you are inheriting ontological commitments that might be heavier than the ones that you had already with the measurement problem in the version of cosmology. So I was wondering whether this shift is actually justified, or is just only a tryout for something like maybe this can be possible, because we also don't have like real data in favor of Bohmian mechanics compared to other interpretations. So what is your take on this?
Yeah, that's a good question, because if we notice, the Bohmian idea is postulates the idea that we have particles, or something like some philosophers call primitive ontology. But that's a problem, because why do we need a primitive ontology? It's ontological commitment very strong, and we can use, for example, something like collapse models that say, well, we don't need a primitive ontology. We can use only wave function and interpret it like a mass density or energy density. It's a philosophical discussion, and my idea is not take some position about the superiority or exclusivity of Bohmian mechanics. The idea is, let's take a look about these problems and how it works with this framework. And also there are a lot of problems. I don't talk about it because it could be more technical issues, but there are a lot of critics. Some people say that Bohmian mechanics is not Lorentz invariance, that breaks the spirit of relativity. There are a lot of problems and philosophical issues in this question. So the idea is that my position is take this framework, and it could explain something that the standard model or standard formalism couldn't. Well, yeah.
Thank you, Victor. Maxine, we have just one last question. Please be brief, the two of you, and please.
Okay, thank you. Thank you for the great talk. It's very clear. So my question is maybe a follow-up for the first, maybe the second question about the modeling the universe as a closed system. So it sounds quite intuitive. So if you think, if we have a metaphysical conception of the universe as everything included, but actually when we talk about closed and open system, we're talking about a way of modeling, right? So a closed system, in the sense, you can think of it as the state space is fixed. So recently there are people like Karim and James Littleman. They're arguing that we should think of the universe as an open system. It's not so it's maybe hard to imagine that if the universe is already everything included, how can it be open? But that's sort of conflating a metaphysical concept with a physical modeling concept. So in terms of physical modeling, an open system just means that it could just mean that the state space of the system of modeling is not fixed, right? So
my idea is not to be exhaustive about the idea of closed system, just that if we apply quantum mechanics, if we apply quantum mechanics as it is, there are so commitments about external.
I think that's also in the sense that whether we can extend the way that we model quantum system as a finite system to the extent of the universe, right? So maybe something have to break there. That's the idea. That's the idea of imagine the universe as a closed system, as a closed quantum system, as we would model it in the lab. That maybe something has to break there.
Mm-hmm. Well, my idea, and I think that it's the idea of the Bohmian theorist, it's that if we don't make this kind of distinctions, we can break something like superpositions. It's just something like, it's a commitment that comes from the standard formalism, that is ambiguous, that is wrong in this sense. So this just illustrates the idea that standard quantum mechanics is wrong in this sense.
It's not. Maybe it's just that when it extends to the scale of the universe, it cannot. There's something has to be different. The similar. For example, the similar argument has been raised for the. So if you extend the thermodynamics to the scale of the universe, you have the path hypothesis, right? But some people will argue that that's the extension, that's the overextension, that's overgeneralization of. So it's hard to define. For example, John Yeaman would say that it's to define the initial state, the entropy of the initial state of the universe is a ill-defined concept.
Yeah.
Right. So there are different ways of looking at where something has to break when we extend our modeling technique to not well specified territory.
Yeah.
Thank you.
Yeah, thank you.